So we're going to finish 9 today and start in on chapter 10, which is our alkyne chapter. And the last piece of chapter 9 is introducing synthesis. Now that we've done substitution and addition and elimination, we're going to put all of those together and work some multi-step synthesis problems. It says the next unit exam is on Tuesday. That's what it says. And so we can talk about that at the end and what we want to do with the unit exam. All right, so we're going to start on page 446. In your book. And so 9.12, which is predicting products of addition reactions. So now that we've gone through all of our hydrohalogenation, halogenation, hydration, hydrogenation, right, halohydrin, we've gone through all of our addition reactions. So we're going to work a problem and figure out, or work some problems and figure out how to decide what your product should be. So the first thing is the identity of the groups that are adding across the double bond. So it's the first thing you need to determine is what are you adding across the double bond. The second thing is regiochemistry. So regiochemistry, is it Markovnikov or is it anti-Markovnikov? And the last one is stereospecificity. So is it syn or anti? Do you create a chiral center? If so, how many? So you have to look at the stereochemical concerns. First question, what am I adding across the double bond with this reagent? Water, right? Is this Markovnikov or anti-Markovnikov? It's anti. Okay, so so these are the two carbons involved in my double bond. So that's where you need to be focusing when you add those things across the double bond. So with anti-Markovnikov, that means your OH is going to the less substituted position, right? Which would be here. Once you have this, do we have any stereochemistry? No, because we're not creating any chiral centers. All right, next one. So what am I adding across? Okay, 2 hydrogens going across. Is this Markovnikov or anti? Okay, it's Markovnikov addition. And this is my hydrogenation. So what I'm doing is I'm adding 2 hydrogens across my double bond and taking my alkene back to an alkane, right? And so, do I have any stereo concerns here? So look at the red carbons. Are either one of those chiral? Yes, the one attached to the ring. And so, when you do hydrogenation, is this syn or anti? Well, it's syn if you have 2. Let me back up. So I'm forming 1 chiral center, 1 chiral carbon, which means I'm going to have a mixture of R and S. If you don't like that, you can draw it, because I'm getting faces. If you don't want to show the hydrogen, you can draw the methyl on a wedge. That makes a difference to you. Doesn't really matter. Okay, let's find another one. What am I adding across my bond? Okay, it's a dihydroxylation, and it's kind of a misnomer up here. So it's not, there aren't 2 things, it's not really Markovnikov or anti-Markovnikov, right? So you don't really have to worry about regiochemistry because you're adding the same thing. So there's no preference on which carbon gets which group. Then we've got regiochemistry. So once I get my OHs on here, what is the orientation? It's syn. Okay? And since there's no plane of symmetry anywhere, there's an enantiomer. So this is not a meso compound. We don't have a plane of symmetry. Questions about these? So when you're trying to predict products for addition, you go through these steps. What am I adding? What's the regiochemistry? And then what's the stereochemistry for my products? The next section talks about synthesis strategy. And we're going to start with 1-step synthesis. And we've gone over substitution, addition, and elimination. These are our categories so far when we talk about one step. For substitution, this is SN1 and SN2. For addition, these are all of our reactions that we've discussed in Chapter 9. And elimination is E1 and E2. So substitution, we're switching out our functional groups. So we're swapping X for Y. For addition, we're adding something across our double bond. And for elimination, we're removing something to create an alkene. So I'm going to write some problems on the board, and you're going to tell me the reagents necessary to accomplish that one-step reaction. Does everyone have this? Are we still writing? Still writing. So what happened on our first one? So I had a double bond. Now I have an alcohol, right? So what did I add across the double bond? So this is addition. What did I add across my double bond? Water. So that's what I added across. Now look at the regiochemistry. Is the OH on the more or less substituted carbon? Okay. It's on the less substituted carbon, which means automatically I know I'm talking about peroxide, right? It's an anti-addition, anti-Markovnikov addition with peroxide. And I only have one reagent that does that. So that's BH3, THF, followed by sodium hydroxide and peroxide. Now what happened in the second one? Which class of reactions am I doing? Elimination, because I'm forming a double bond. And what am I removing? hydrogen and a bromine, right? And what would I use to do this? So this is an elimination. Is this a Zaitsev or Hoffman product? It's Hoffman, right? So that means it's E2. Remember, base selective. And that means my base is tert butoxide, because it has to be a sterically hindered base. Okay. What's happening in E? So anytime you go from a double bond to having a functional group, that's addition. So this is addition. What am I adding across my double bond? Chlorine, and the thing you don't see is hydrogen, right? And what is my regiochemistry here? It's Markovnikov, so it's going to the more substituted carbon. So what would I add here for my reagent? Just HCl. So not so bad, right? So these are our three main categories of reactions that we've looked at. So Chapter 7 was substitution, Chapter 8 was elimination, Chapter 9 was addition. So we've had a chapter for each one of these. So what if I want to change the position of a leaving group? And or the identity of the leaving group. So there's a pattern for this. If you want to change the position and or the identity of the leaving group, then you would do an elimination followed by a substitution, not a substitution, an addition. So this is a pattern. Elimination, addition. So you're taking the current leaving group off and you're going to put another leaving group on. So this isn't a case where you're moving it, it's not. So if my leaving group is here on carbon 2, right? A substitution would be swapping my functional group on carbon 2. But that's not what I'm doing. I'm moving the functional group from carbon 2 to carbon 1 or carbon 3. So it's relocating. In order to do that, you have to take it off and form a double bond and then do an addition reaction across that double bond. So it's 2 steps. So for example, if I treat this with sodium methoxide, then I'm going to get the Zaitsev product, right? If I treat this with tert butoxide, I get the Hoffman product. This is important because then if I add HBr across, where is it going to go? So I've moved the bromine from this carbon to this carbon, right? So I have moved the bromine down the molecule. What if I add HBr and peroxide? Where does it go? So it goes on the end. So that would be moving it from here to here. So depending on where you want to relocate your functional group, you pick the base, do the elimination, and then you have to pick your addition reagent to put it preferentially which functional group you want and where do you want it. Does that make sense? So you have to think about where am I currently and where do I want it. And so that's your choice of base to how to take it off. And then your next step is what functional group do I want to put back on and where do I want that functional group, and that's how you choose which addition reaction you do. What if I start with, instead of starting with bromine, I start with an OH. And I want to make this primary halide. What do I treat this with? So think about the mechanism. You have a leaving group, right? And a proton transfer. Is this a good leaving group? No. When you want to do an elimination and you start with an alcohol, you always have to convert that to a good leaving group first. So the first step is going to be, you're going to treat this with a tosylate chloride and pyrimidine. And that makes a good leaving group. Then you can treat it with your tert butoxide. Because otherwise, think about, alcohols are stable, right? So they're awful leaving groups. So if you want the alcohol to come off, you have to convert it to a good leaving group first. Okay. Questions here? Alright, so let's work a few of these. First thing you want to do is identify the carbons involved in your reaction. So, these two carbons, right? Then you want to know what type of elimination are you doing. Is it Zaitsev or is it Hoffman? Because that's going to determine which base you choose, right? Then, what functional group are you adding? Because that tells you the reagent, or at least the mechanism, and then within that mechanism you can pick which reagent. So which functional group is added, and kind of these two go together. What is the regiochemistry? What type of elimination are you doing? So is it Hoffman or is it Zaitsev? So if I'm looking at this, so we know which carbons are involved, so the red ones, and then which one, what type of elimination am I doing? What's my product here? It's going to be Zaitsev because it's going to the more substituted side. So my first reagent is going to be a strong non-hindered base. So sodium methoxide, sodium methoxide, sodium hydroxide, any of those work. Alright, so if I treat this, so now I'm here. So how do I get this? Okay. So I'm adding 1 chlorine, which means HCl, and it's going to the more substituted carbon, which means it doesn't have peroxide. So it's just HCl. So my OH is moving from here to here. So those are my 2 carbons, right? And if I'm looking at the type of elimination, is this Zaitsev or Hoffman? It's Hoffman. It's going to the less substituted side. So that means that my base has to be but what's my first step? Is this a good leaving group? No. So step 1, convert to a good leaving group. Step 2, treat with the sterically hindered base to get the alkene. So now, what functional group have I added across my double bond? Water. So I've added water across my double bond. And if I'm looking at orientation, the OH is going on the less substituted carbon. So remember, for hydration, you have 3 options. You have acid catalyzed, so that one does carbocation rearrangement. Then you have mercury, which does not, but both of those are Markovnikov. And then you have your hydroboration oxidation, which is anti. So BH3, THF, followed by your sodium hydroxide and peroxide. So 3 and 4 go here. So that's moving a functional group. So doing an elimination followed by an addition. The next thing that we need to look at is changing the position of a pi bond. So changing the position of a pi bond. So I've moved my pi bond. So the first thing, so your pattern here is addition, followed by an elimination. So addition followed by elimination. So it's the same rules as before, almost. So you identify the carbons that are involved. Then you have to determine the reagent used in the addition reaction. So look at the regiochemistry and the stereochemistry. Right over there. Oh yeah, there you go. Determine the type of base you need for the elimination. So I have my carbons and I'm putting the bromine on the less substituted because there are three carbons involved in this. So if I'm looking, my double bond initially is between these two carbons, right? The green ones. And you're moving it to the end. So there are 3 carbons involved in this process. So the 2 initial and then the 2 final. It just so happens the middle one is involved in both double bonds. So that's where you have to put your leaving group. So whichever carbon is the swing carbon, the one in the middle, that's where your functional group has to go. So these 3 carbons are involved in my reaction. So the ones on the left initially involved in the double bond, and then the ones on the right involved in the final double bond. The one in the middle is the one where I have to put my leaving group. So remember, this is addition and then elimination. So if I'm looking at this carbon, that's where I want to add my leaving group, is this, what's the regiochemistry here? Am I adding Markovnikov or anti-Markovnikov? Markovnikov. Because it's the more substituted of the two. Okay? So something goes here. What do we want to put there? Doesn't matter. I'll put a bromine there, HBr. Okay? So bromine goes on, and then bromine has to come off. So I did an addition, now I have to do an elimination. What type of elimination is this? Is it Zaitsev or is it Hoffman? It's Zaitsev. So we want a non-sterically hindered base. So sodium hydroxide, ethoxide, methoxide, it doesn't matter. Any of those will work. Do we want to do another one? Okay. How many carbons do we have involved in this one? 4. So guess how many cycles we have? So I want to put something on this carbon. So I'm just going to draw a generic map of what I want to happen. I want to put something here, and then I want to take that off. So I have 2 cycles of addition, elimination, addition, elimination. So what do I need to put on for the first round? So we'll call this reagent 1. What needs to go here? A halogen. Okay, you want a good leaving group. And would this be Markovnikov or anti? Okay. So you had HBr, so you would put a bromine here. So you're going to take your bromine off and make your double bonds here. So is this a Zaitsev or a Hoffman product? It's a Zaitsev. So sodium methoxide. Then I need to put a halogen on that 3rd carbon. How do I do that? Is this Markovnikov or anti-Markovnikov? Anti. So that means it's HBr and peroxide. To put the bromine here. And then I'm taking it off. And is this Zaitsev or Hoffman? It's Hoffman. That means my base has to be tert, right? Tert. To give me the sterically hindered base to give me my final product. If you'll flip over to page 454, there's a reaction map, and so that's all of the reactions that we've learned in this chapter, and that will be helpful for you to draw out and just kind of get yourself familiar with what that looks like. There's some homework problems as well that do that, so 49, 50, 70, 71, those are all good problems to work through to kind of get these individual reactions down. So that is the end of 9. Any questions on that before we do just a teeny bit on 10? No? Okay. Chapter 10 deals with alkynes. And alkynes are sp hybridized. And that triple bond has 1 sigma and 2 pi bonds in it. The simplest alkyne is C2H2, and this is acetylene. And acetylene is used in various things to make compounds, kind of the starting point for a lot of synthesis for alkynes. It's also used in welding as a fuel for torches, and it burns at about 2800 degrees Celsius. So if you've seen the acetylene torches and people wearing the big masks, that's what they're using for fuel for those. There's a medically speaking box, and it talks about a drug and that's used to treat Parkinson's, and it has an alkyne in it. So it's usually prescribed in combination with L-DOPA. This is an MAO inhibitor, and so MAOs break down the dopamine, and so that just makes the drug last longer in the system. So you give L-DOPA along with the MAO inhibitor, and that helps that drug last longer as it's going through the system. Typically, these are analogs of a natural compound, so that bind to the enzyme and inactivate it for a short period of time. Of course, we have a new thing, so we have to name it anytime we get a new class of compounds. These naming rules for alkynes are very much like your alkenes. So you have to ID the parent chain, and the parent must contain your triple bond. And it gets a YNE ending. So if it has 4 carbons, it would be butyne. Then you ID and name your substituents. Number your parent and assign locants. And just like our alkenes, the triple bond gets preference. In other words, it gets the lowest number. Regardless of the substituents, your triple bond gets the lowest number. And then a symbol name A to Z. So 5 carbons. Be careful with alkynes and the number of carbons. I find that it's easy to lose a carbon with the alkynes because of the bond angles. So remember, the bond angle between these 4 atoms is linear. It's 180 degrees. It's fixed. It's very rigid. So if I'm looking at this, this is 1, 2, 3, 4, 5 carbons. It's easy to miss this one. So make sure that you keep in mind that there's a linear, those 4 atoms are in a straight line from each other. So you've got four atoms there. So you would have a hydrogen out, right, that's not being shown at the end. So you would have 1, 2, 3 carbons and a hydrogen that are all 180 degrees. All right, let's do a little naming really quick. So there are 6 carbons. That makes this hexine. And the triple bond is on carbon 3, so it will be 3 hexine for the first one. 1, 2, 3, 4, 6. So this is also so what are my numbers here? So it's on carbon 3, and what substituent do I have? I have a methyl group, so that would be 2-methyl 3-hexine. So this would be 1-butine. And what are my substituents? I have 2 methyl groups. So what number are they? 3. So it will be 3, 3, dimethyl 1-butine. There are 2 types of alkynes here. This is an internal, meaning the alkyne is sandwiched between 2 other carbons. So this is internal. This one is terminal. So a terminal alkyne is at the end of the chain. It has a hydrogen out here. Guess what? That hydrogen is fairly acidic, so it's very reactive. We're going to be doing lots of reactions with that hydrogen that's on our terminal alkynes. We'll do a little bit with the internals too, but this one comes into play a lot in the future. Okay. So let's